Hi guys, now I would be focusing into rolling of a body without skidding down the inclined plane. Alright, I would be first explaining you all the formulae required for these type of numericals. I would explain you very well, very clearly, and once I've explained those formulae, would be applying it also in numericals for clarity. And later on, I would definitely derive all these formulae, but that would be the theoretical aspect. In physics, it is numericals which are more significant to understand. Keeping that in mind, I am carrying on this process. So you would have a series of numericals now based on rolling body down the inclined plane without skidding or slipping. Alright, happy viewing. Okay, let's get into understanding formulae for rolling motion without slipping or skidding. Now it's rolling, so it won't skid like that, it would keep on rolling. There shouldn't be any skidding or any slipping. Okay, so it has to roll like that and come. So that's what is the requirement. Alright, now prior to getting into this, let's understand something about radius of gyration k. It's distance k from center of mass of body, where whole mass of body is assumed to be concentrated, and it is mk square. Now suppose if I draw a body here like that, a body like here. Now it's rotating. The body is not a regular body, it's an irregular body. So we assume that probably at this distance the mass is focused. Alright, and since it's rotating, so this becomes the k, radius of gyration. So when it is rotating, this becomes the k, that is the radius of gyration. So let me read again. It's distance of k from center, it's distance of k from center of mass of body, where whole mass of body is assumed to be concentrated. Alright, so that is what is k, that is what is a radius of gyration. Alright, so how do we correlate radius of gyration with moment of inertia? Alright, now let's check it out. Now if I say for disk, we know that it is half mr square, IC is half mr square, so that would be equivalent to mk square. So this would be all I, right? It would be equal to mk square. So what happens? We know this gets cancelled. I root on both the sides. Now when I root on both the sides, r square becomes r, k square becomes k. So our formula for radius of gyration for disk is r by root 2. Similarly, if I pick up for solid sphere, we know IC is 2 by 5 mr square, which is equal to mk square. This gets cancelled. Again the same thing. I take root of the entire thing. Root of the entire thing, so it becomes root 2 by 5 r square, so it becomes r, and k square is k. So radius of gyration is root of 2 by 5 r. Similarly, if I go for ring, it is mr square, which is equal to mk square. Obviously m gets cancelled, then I do root of both the sides, so k is equal to r. So these are all the radius of gyration. So this is the radius of gyration for disk, and this is the radiation, this is the radius, this is the radius of gyration for solid sphere, and this is the radius of gyration for ring. So radius of gyration for disk is this, radius of gyration for sphere is root 2 by 5 r, and for ring k is equal to r. Alright, now let us see, as I told you, understand this formulae well, then we can sort in numericals very easily. Derivations and all would go on, alright, one by one. Alright, so but it's not essential for you to know derivation for solving numericals. So what I am doing is I'm just making you understand all those formulae required for numericals. Okay, fine. I am talking about a rigid body which is rolling down the plane, which is at an angle theta, and this height is h, has a radius r, and has mass m. Alright, and it is not slipping, it's rolling, it's not skidding. Alright, so that's the requirement. Now let's talk in terms of total kinetic energy. So from here to here. Now see, this is what? This is the linear motion. Now formula for kinetic energy for linear motion, for linear motion is half mv square, and there is rotational motion also. So we also have got to have kinetic energy for rotational motion. I we know is m, we know is I in rotational motion. Linear mass is equal to I in rotational motion, and v is equal to angular velocity. Linear velocity is angular velocity. So this is translational motion, this is rotational motion, kinetic energy. Alright, some of that we do. Now we know that v is equal to r omega. That's what I taught you earlier. So omega is equal to v upon r. Done. So we can jolly well substitute over here. That's what we did. So it is. And mind you, again, here also I need to explain you. Here I is also equal to mk square. We are talking in terms of radius of gyration. That's the reason why I taught you what is the radius of gyration. Okay, so we would be using radius of gyration. Fine. So we use here radius of gyration. So here I have got radius which is there. Okay. So half mv square plus half mk square v square over r square, where k is radius of gyration of that object. Alright. So what do? We take half mv square common of bracket. So what remains is here this 1, and here what you have is m and v square is out, half is also out. So what we are left with is k square over r square. So this becomes our first formula that you have got to keep in mind in terms of kinetic energy for a rolling motion of a body without slipping. Alright, so that's what is one. Now another, for velocity of this body, a rolling body without skidding, 2gh upon 1 plus k square over r square under root. Alright, so that's what is the formula which you have got to keep in mind. R is radius, k is radius of gyration. So whenever you are having any such equation, so you can substitute, whether if you are finding a disk rolling down, then in that case, if you want to substitute k, instead of k you can substitute this value. So it will become, so here it would be r square into 1 over root 2. Alright, so r square r square cancel, 1 plus 1 upon root 2 would remain, and do that and then do the calculation. G we know is gravitational acceleration, h is height which is given. Alright, similarly if you want to talk about a ring which is sliding down, so in that case ring, we know radius of gyration is r. So if you want to substitute over k, r, it all depends on you. So if you want to substitute radius of gyration, instead of k we can put it as r square. So r square gets cancelled, so it becomes 1 plus 1 2 cancel. So the formula becomes root gh for ring. Alright, we would be solving numericals. I'm just giving you an example how to apply this formula. Alright, okay. Then again, if we are intending to find acceleration, then this is what we have got to use. This is the formula. G sine theta upon 1 plus k square over r square. That's the formula. Now, what have I done? I have just this h sine theta is equal to h over s. So s goes there. So h instead of h, we can also write it as s sine theta. So this also becomes our formula for height. Alright, so that is alright. So s sine theta and so on and so forth. So that I'm just telling, right now we are not using that, but while derivation we will be using that, and for that I'm clarifying h is also equal to s sine theta. Why? Because we know sine theta is opposite over hypotenuse, opposite is h, hypotenuse is s, so h is equal to s sine theta. That also is the formula. So these are the things that you have got to keep in mind to proceed for numericals. Okay.